Morning, everyone. Glad to give this talk at SREcon Asia. Before I enter the topic, I'd like to give a brief self-introduction. My name is Xianping Qu. I'm a manager of Baidu SRE team. And this one is Jingjing Ha. She is a senior software engineer in Baidu SRE team. And our focus areas are operation platform development and improving the operations efficiency. Today, our topic is AIOps, which is, we believe, is the next generation of DevOps. We will also introduce our best practice based on AIOps. Maybe some of you are not quite familiar with Baidu, so please let me introduce my company first. Baidu is the largest search engine in China and is the largest Chinese search engine in the world. Besides search engine, we also have many other products, such as forum, map, wiki, and open cloud and personal cloud storage. And we have over 100 products and over 10,000 engineers. Our team, Baidu SRE team, has over 400 engineers. This page is our outline. Firstly, I will introduce the history of Baidu SRE team. Next, I will introduce our operations framework, whose name is AIOps in detail. This part will focus on the components of the framework, including operation knowledge base, open development framework, and algorithm platform, as well as how to use this platform to develop reusable and scalable operation tools more efficiently. Then, Jingjing will introduce our best practice based on AIOps framework. At last, she will give a brief summary of our present work and future plan. Baidu SRE team was established in 2007. Early on, our members were all ops, and we were operation teams. Naturally, we have taken practice in DevOps. It's a good idea to have the development people work closely with the operational people. However, with the fast growth of Baidu products, a problem came to us. Our OP engineers quickly became overburdened. Their daily tasks include deployment, monitoring, budgeting, and consulting. All these tasks are in a very primitive form. For example, when we make a deployment, what we get from the developed software engineers is a Word document. We have to paste every line of the deployment command from the Word document to the console. This is laborious and error-prone. It is of the utmost urgency to improve the efficiency of operations. Thus, we began to automate the manual actions. We built a new team, which is mainly responsible for operations systems research and development. During the years from 2009 to 2012, we developed many systems, such as service management system, monitoring system, deployment system, traffic scheduling system, and naming service, and so on. With the development of these systems, ops have been liberated from the heavy basic operation tasks. However, a new problem came to us. Most systems only provide interface for human interactions. When the number of tasks grew even larger, operating on the graphical interface still costs too much time. For complex tasks that depend on multiple system, engineers have to manually coordinate the system properly. Our solution is to transform our system to platforms. Our platform not only provide the interface to interact with humans, but also provides a set of APIs to interact with other platforms or systems. Thus, the previously isolated system can be combined to support complex tasks. Moreover, the platform also extended human interface to allow the engineers use configuration files and scripting to control the platform's behavior. For example, our monitoring platform supports to use JSON and SVN to manage every product's monitoring configuration. For another example, is our deployment platform provides scheduling API to other platforms and systems so that our incremental deployment supports different products use different scheduling policies. However, there was still a problem that have not been solved. We found that many platforms only work for a few products. The main reason is that different products adopt different operations, object description, different method of product management, and so on. So we began to do our standardization solution. There are 3 core components in Baidu's standardization solution. First, unified language. We design a unified operations language. For example, how to describe a service status, a cluster's capacity, service availability, SLA. Second, we design a unified operations method. For example, when building an operation plan, we should let all ops use the unified operations method to build the plan. Lastly, the unified operations solutions can be built based on the unified operation language and operation method. Now, everything seems to be perfect, except that it is a robot, but without a brain. So after 2014, we began to develop a new platform, more accurately described as a framework. AIOps, a term recently coined by Gartner, refer to solutions that use artificial intelligence and machine learning to automate tasks and processes that have traditional required human intervention. In Baidu, this AIOps framework needs 3 parts. First is development framework, and second is big data, and lastly is algorithm, like data mining and machine learning algorithm. And in the first part, development framework, there are 2 main points. First, we must package the most commonly used operating methods or API. Second, we also need to provide a develop kit of operating tools to our ops, which includes toolchain, simulation, and runtime environment and other tools or environments. In this way, engineers can easily experiment their AIOps modules. Then we also need a big data solution. A big data solution requires an operation knowledge base. There are 2 main parts in our operation knowledge database. First, operation data models abstraction. We need a standard data schema. Without a standard data model, the machine learning algorithm cannot effectively use them to make decisions. Second, the operation knowledge base becomes to the only authority data source so that all data consumers can find the correct and integral data here. Besides the development framework and our operation knowledge base, we also need to support many data mining and machine learning algorithms, such as anomaly detection, root cause analysis, and trend forecasting. Ops can use this algorithm to develop automatic and intelligent operation tools themselves. Now, our solution can be shown in this figure. The yellow parts are AIOps framework, and Ops can develop operation tools, algorithms, systems, platforms, or solutions based on it. In the following, my colleague Jingjing will introduce our practice based on this solution.
Okay, in this part, I will give 3 practices to show how to build operation application based on our AIOps model to improve the quality and the efficiency of certain operation jobs. First one, in the incident management topic, we achieved a single cluster stop loss by traffic shifting without any manual intervention. And in the deploy management topic, we use the automatic checker to implement unattended deployment. And the automatic checker improves the checking efficiency and successfully limits the failure into a single cluster. And then the last one is in the consulting topic. We attempt to apply natural language processing technologies in our daily work. And the resulting chatbot is able to answer some popular questions, save a lot of our engineers' time. First of all, I will introduce our single cluster stop loss practice based on our AIOps model. So loss is caused by failures. When a failure occurs, it can be divided into the 4 typical reasons. The first one is the infrastructure issue, such as the server failure and network device failure, and sometimes the traffic forwarding service failure. And the second one is the program defects. So some bugs can sneak out of our testers' hand because only specific requests can trigger out the bugs. But when the bugs are released into the production system, and they usually hide for some time and burst out suddenly. Another scenario is that the system performance could degrade significantly because of the incomplete stress test and the difference between the test bed and the production bed. The third one is the change exception. In the past years, we have experienced numerous changes that lead to serious failures. Part of the failures relate to the insufficient test. And the testing should cover not only the changes of the programs, but also include the data change and the configuration changes. Still, some other failures are caused by the SRE engineers' careless actions. And the last one is the dependent service unavailable. The dependent service could be third-party service, such as central authentication service provided by social network companies, and the payment service provided by online commercial companies. And the dependent service also includes some infrastructure service provided by our internal departments, such as the cache service, a storage service, and computing service, and so on. Since failures are unavoidable, we need to find a way to minimize the loss. And our approach is traffic shifting, and our appearance confirms it's practical and effective. Traffic shifting has two basic Traffic shifting has two basic requirements. First one, we should limit the failure into one cluster. And the second one, we should provide redundant resources to receive the shifted traffic. In order to limit the failure into a cluster, we need to adopt the following three principles. First of all, deployment isolation. Deployment isolation can avoid one data center failure cause multiple service cluster failure. And there must be no single point service and no service deployed across multiple data centers. A second one is the dependent decoupling. Dependent decoupling can avoid cascade failures spread from dependent clusters to multiple supported clusters. And when there are abundant resources, we always deploy a copy of the dependent service together with the supported service cluster in the same data center. But most of the time, the service is very limited. And in this situation, we require the traffic between the supported service and the dependent service can be freely shifted among the copies of the dependent service. A third one is the reduce the global risk. We need to set global locks. In order to prevent the program and data and the configuration changing from applying on all the clusters at the same time, we need to check status after each stage of changing and stop the deployment when any failure occurs. So another requirement is capacity redundancy. When talking about capacity redundancy, we know that availability and cost is always a trade-off. We want to achieve M plus M redundancy in order to tolerate M cluster failures. But most of the time, M is only allowed to be 1 because of the limited resources. In some extreme cases, service degradation can reduce the consumption of resources and to tolerate one cluster failure. After both the two requirements are satisfied, we can perform traffic shifting when a cluster fails. Let's see how a product responds to user requests in the Baidu's deployment architecture. First, the user client requests the DNS server to obtain the corresponding virtual IP address of the domain name. And then the user client reads the virtual IP address, and the traffic arrives at the BGW. BGW is a Baidu gateway, which is a layer 4 load balancer. And then BGW forwards the traffic to BFE cluster. BFE cluster is a Baidu front end, which is a layer 7 load balancer. Then BFE forwards the traffic to the web service cluster, and the web service cluster calls the dependent service cluster and generates the response. The response goes through the BFE BGW cluster and the internet, and finally arrives at the user client. So in this architecture, we use two-layer traffic shifting strategy. The first layer shifts the traffic between the user set and the agent node by changing the binding relationship of the domain name and the virtual IP address. And the agent node refers to the entrance port from the ISP to our data center. The second layer see the traffic between the front end and the back end by changing the routing configuration of our BFE cluster. So that's our two-layer traffic shifting strategy at Baidu. And the shifting traffic between the user set and the agent node can resolve all the single cluster failure scenarios, but it requires more time to come into effect. In our practice, it costs about 10 minutes to shift 18% traffic to the healthy agent node because of the DNS cache in the client side and the ISP side. And shifting traffic between the front end and the back end is more efficient, but covers only part of the single cluster failure scenarios. we can achieve about a 10-second delay to shift the 100% traffic to the healthy backend by changing the routing configuration of our BFE cluster. So I will share some single cluster stop loss scenarios in detail. The first scenario is the shift traffic between the front end and the back end. When failures occurs at the web service cluster, the dependent service cluster, and the network devices between these two clusters, shifting traffic between the front end and the back end can stop loss. This traffic shifting strategy is restricted by the service capacity and the internet bandwidth. It costs only 10 seconds to take effective, but sometimes we use a progressive traffic shifting strategy to reduce the risk of the capacity overload. Another scenario is shift traffic between the user set and the edge node. When failure occurs at the entrance of the network devices at our BGW cluster and the BFE cluster, traffic shift between the user set and the edge node can bypass the broken infrastructure. And this traffic shifting strategy is restricted by the bandwidth, the BGW and the BFE cluster capacity, and sometimes the user response delay. In this scenario, if the web service cluster's capacity is not enough, and the traffic between the front end and the back end will be automatically triggered by our load balancing strategy. The last scenario. So in the cases that the entire data center fails, such as the power outage and code switch failure, two-layer traffic shifting will be triggered together to stop loss. So that's all about our scenarios. We can see that the single cluster stop loss process can be divided into 3 stages: perception stage, a judgment stage, and the execution stage. In the perception stage, we discover failure from the monitoring system. And in the judgment stage, we make a stop loss plan based on the failure scenarios and the load situation. And in the execution stage, we execute traffic shifting and service degradation operation and checking the execution results. The current single cluster stop loss process have some drawbacks to be optimized. For example, in the perception stage, handcrafted anomaly detection in the traditional monitoring system results in loss of false negatives and false positives. In the judgment stage, decisions are made manually based on personal appearance and based on partial information. And less experienced engineers occasionally made wrong or slow decisions, and this results in more losses. When the judgment must be made in a very short period, and engineers may not adjust the stop loss strategy carefully enough. In this situation, single cluster failure may spread into multiple clusters. A typical scenario is the capacity overload during traffic shifting. And in the execution stage, current stop loss commands are parted into poorly coded scripts and scattered in different places. And we have experienced several cases that the scripts fails to carry out the decisions correctly. So because of the above serious problems, we reconstruct the single class stop loss solution based on our AIOps model. In perception stage, we use intelligent anomaly detection to obtain high precision and recall. And the abnormal events are stored in the operation knowledge database, which provides high availability and low delay interface to the following stages. And in the judgment stage, we built a accurate and quick decision program based on our algorithm platform, and with feedback control, the risk of the capacity overload during traffic shifting can be reduced. And in the execution stage, we define standard framework to code the scripts and run the scripts on the unified deployment framework. And reliable scripts can reduce the risk in the automatic stop-loss process. So this picture shows the architecture of our single cluster stop-loss boss. The perception platform consists of a series of monitoring systems, such as network monitoring, business monitoring, and application monitoring. And these monitoring systems generate the abnormal events. And the judgment platform consists of two stop-loss decision-making boards. One board is the virtual IP traffic control. It is responsible for making decisions about how to shift traffic between the user set and the edge node. And it subscribes the abnormal events of the BGW, BFE, and the network devices. And then it identifies the failure virtual IP address and modifies the mapping from the domain name to the virtual IP address. And then our DNS configuration management system carries out the change automatically. Another board is the service health control, and it subscribes the abnormal events of the web service cluster and the dependent service cluster, and it coordinates the stop-loss operations of the shifting traffic and downgrading service based on current load situation. And the commands are executed by the stop-loss execution boards. And we have an internal traffic load balancer. Internal traffic load balancer progressively applies traffic shifting based on real-time load data, and it makes a trade-off between the loss of the failure cluster and the overload risk of the healthy cluster. So our algorithm platform provides anomaly detection algorithm and the traffic shifting algorithm for our stop-loss boards. And the operation knowledge database provides the infrastructure to achieve the storage, subscription, and query of the abnormal event, metric data, and the capacity data. So that's all for our single cluster stop-loss practice. And in the next, I will introduce our unattended deployment with automatic checker. In a deployment process, service health status must be checked at strategic moments. For example, before the deployment, after one instance deployment, and after one cluster deployment, and so on. And the checking results determines whether the deployment will continue or roll back. And we build an unattended deployment platform with our automatic checker based on the AIOps model. And it can improve the checking efficiency and successfully limit potential failure into a single cluster. Our automatic checker experienced two stages of evolution. The first stage changes the manual checking method to anomaly detection-based method. The manual checking depends on multiple manually configured dashboards, and each dashboard is composed of multiple monitoring metrics, while in the anomaly detection-based method, a single dashboard of the abnormal events is enough. And the second stage is changing the method further to the automatic API and API checking and automatic the notification based on our operation knowledge database. And with this unattended deployment platform, we have greatly improved our deploy efficiency. The last scenario is our chatbots. In Baidu, some consulting jobs are taken over by chatbots to save our SRE engineers' time. And the questions chatbots can answer are very diversified, such as who is on duty, who is the owner of the module, and what's the status of the network service, and so on. And I will give an example. For example, a common questions type is maybe like this. Is there any change on module X today? And then we employ the natural language processing technology to transform these natural language questions into a structured query. And our AIOp model identifies the question's intentions as change query, and the module in concern is X, and the time of the change is today. So then this query is submitted to the operation knowledge database, and the relevant change events are then returned to the user. From the example, we can see that in order to build a chatbot, we need the following steps. First one is accumulate manually labeled questions. And the second one, train an AIOp model to understand the questions. A third one is translate the natural language questions into a structured questions. And the fourth one is query our operation knowledge database, and then display the results at SRE service desk by a user-friendly method. So that's all of our practice. In the past minutes, I have introduced our AIOps practice of the incident management, deploy management, and the consulting topic. So what's the next? In the future, we attempt to solve dynamic resource allocation, capacity management, and identification of performance problems based on our AIOps model. And we believe with the innovation of the technology, the efficiency of operation job will be greatly improved. So SRE engineers will be free from the time-consuming, cumbersome basic operation jobs, and they can contribute to solve some more difficult problems. So that's all for our talk.